Hi, so we're going to start chapter 6, solving differential equations using series, and in particular power series. Well, in some cases, in other cases it's just a generic infinite series. And so in section 6.1 we're not going to be solving differential equations yet. We're just going to be reviewing power series. And for most of you, I wouldn't even think of this as a review because it might have been a while since you've had Calc 2, where you were introduced to power series. So I'm not exactly sure how confident some of you are on power series. So I'm going to go through this very carefully because if you don't have a complete mastery of power series, then the next two sections are going to be very difficult. So yeah, I'm going to go through this carefully and review everything you need to know about power series that will help you through the next two sections. And so let's start with just what is a power series. So a power series, right, is, well, anything that has the following form. So it's going to be a series, which means it's going to be a sum. So remember, this is the symbol for a summation, a capital sigma, right? And we're going to start, so for the time being, I'm going to use the index n, but this is, remember, n is like a dummy variable. We could use other letters for the indices, I, j, k, and so on. So n starts at 0 and goes all the way to infinity. And then we have some constants, we'll call them Cn, times x minus a, and again a is just a constant, all to the power n. Okay, so anything that looks like this, where the Cn, right, so Cn's are just real numbers. So Cm's are real numbers. I mean, they could be complex, but let's not get into that, right? And in particular, x are going to be real numbers, right? So this is a power series centered at A, centered at x equals A. And for most of our series, our center is going to be 0, so this is just going to be x to the n. But for the time being, in some cases we might want to shift from x equals 0 to x equals a, right? So this is just the shorthand way of writing out, well, starting at n equals 0, this is just C0 times x minus a to the 0, which is 1, right? Plus, and then when n is 1, this is C1 times x minus a to the 1, right? Plus C2 times x minus a squared, and so on, right? This just keeps going forever. Okay, so that's what a power series is. And remember, when you're taking the sum going to infinity, you have to worry about whether this thing even makes sense. In particular, when you're adding up a bunch of quantities here, a bunch of things, how do we know that that isn't just infinity? How do we know that it even converges, right? So, so this series, we say that this series converges if the sum, the finite sum, right? So if you just take the sum n going from 0 to, say, capital N, right? So here you're ending, right? You're starting at C0 plus C1 x minus a plus dot dot dot, and then we end at C capital N x minus a to the capital N, right? So essentially you just get some sort of a polynomial here, right? So if we call this capital S sub n, and it's a function of x, right? If this capital S actually has a limit, right? In other words, if you take the limit as capital N goes to infinity, right, that this limit exists. And if it does, then the series converges. Okay, so yeah, we do have to worry about, you know, if this is infinite or if it just fails to exist. And it depends on x, right? So this limit might exist, so the series might converge for some x, but not for others, right? So that brings us to the idea of the interval of convergence. And the interval of convergence is just all the values of x where this converges. And it's typically centered at A, so it's going to be the following set. It's going to be the set of all x, right, all real values x, such that, such that the absolute value of x minus A is less than some number, we'll call it capital R, right? And this is really just the interval from A minus R to A plus R. Right, and it could be a closed interval, could be an open interval, could be half open, half closed. For now, we're just going to use the open interval, and then you may remember you have to check whether you can include the A minus R or the A plus R, but here they're not going to be included, at least for the time being. And so this capital R is called the radius of convergence. Right. So it's how far away you can get from A, right? And if A is 0, you're just going from minus A to plus A, right? So, yeah. Or, sorry, minus R to plus R. Yeah, if A is 0. Okay. Right. And, right, there is the possibility that, well, there's three possibilities, right? R could be 0. R could be 0. In which case, in this case, you would actually use the closed interval here because then the series does converge. We have convergence, but only at one point, only at x equals A. And that's pretty useless, right? When the series only exists for one value of x, that's, essentially it's not a function, right? We'll talk about that later, but it's kind of useless at that point. R could be some finite number, say R bigger than 0 but finite, right? And then you really do have this interval here, right? Or R could be infinite, right? R could be infinite, in which case it converges everywhere, from minus infinity to infinity, right? So then it converges for all real numbers, and that's the best case scenario, right? That's what we want to have happen. It converges, right, for all x. Okay. Unfortunately, they don't always converge at all x. In fact, some only converge at one point, which is not ideal. Right. Right. So if this limit does not exist, of course, then the series diverges, right? And that can happen too, right? But when it does converge, it either converges at a point on some finite interval, right, from A minus R to A plus R, or it converges for all x. Okay. So how do we find this radius of convergence, right? Again, the value of A will be clear based on the series, but finding the radius is not always that simple. But there is one way that is you could try, and that's the ratio test. So again, this is something you may remember from Calc 2. If not, let me remind you. We're going to take the following quantity. We're going to take the limit as n goes to infinity of the absolute value of the following quantity. We're going to take, in the numerator, Cn plus 1 times x minus A to the n plus 1 over Cn times x minus A to the n. And just take the absolute value of the whole thing there. Right. And we can simplify this. What's going to happen is that, right, n of these will cancel, and you're just left with x minus A in absolute value. So the absolute value of x minus A, right, we can take that outside the limit because it doesn't depend on n, and then take the limit as n goes to infinity here right, of just the ratio Cn plus 1 to Cn. Okay. Right. So again, assuming this limit exists, let's just call it L, right, for limit. And there's three possibilities, right? One is that right, your L, your limit, is less than 1, in which case the series converges. In fact, it converges absolutely. And remember, if it converges absolutely, then it converges, right? It could be that L is bigger than 1, in which case the series diverges, right? And what happens if L happens to equal 1? Well, unfortunately, we don't know, right? So the test basically just is inconclusive. So the test doesn't work. The ratio test won't work here. So that could happen, but more often than not, it'll be clear that the series converges or diverges based on L, right? Yeah. So again, because it's been a while since you've done this, let's look at some examples here. Okay. So first example. We have, and this is in section 6.1, this is actually number 4 in the exercises. Find the interval of convergence for this series here. So the sum n goes from 0 to infinity of 5 to the n over n factorial times x to the n, right? So we should recognize that this fraction here, that's our Cn, right? So Cn is just 5 to the n over n factorial, right? And a is 0, right? A is 0, so this is centered at x equals 0. Like I say, most of them will be, but not all. All right, so now let's just calculate what L is, right? So let's calculate this limit as n goes to infinity, absolute value. So Cn plus 1 then is just 5 to the n plus 1 divided by n plus 1 factorial, right? And then divided by, well, so, all right, so why don't we flip this over here, right? Oh, yeah, before we do that, maybe I should include that this is just x to the n plus 1, right? All right, so yeah, x to the n plus 1. Right, so that's Cn plus 1. All of that is Cn plus 1. Now we have to divide by, right, this right here, the Cn x to the n. And so when you divide, you're multiplying by the reciprocal, right? So the reciprocal of this will be, right, 5 to the n in the denominator, and then n factorial in the numerator. And then the, right, x to the n will be in the denominator. So, yep, I just multiplied by the reciprocal instead of divided. Same thing, right? So what is this going to end up being? So we still have to take the limit, of course. So we have the absolute value of, notice, the 5 to the n plus 1 divided by 5 to the n is just 5, right? And, well, okay. This is 5 to the n plus 1 over 5 to the n, right? These are 5s, not s's, right? So yeah, that's just going to be 5. And then we have n plus 1, right, factorial, which is n plus 1 times n minus 1, and so on. So n plus 1 times n factorial. And you can see that n factorial is going to cancel here as well. And then we just have, right, x to the n plus 1 divided by x to the n. And so that's just going to be x. So let's simplify all that down here. So this is, still have to take the limit, right? So this is just going to be 5 over n plus 1 times x. And since x doesn't depend on n, we can take the x outside and then take the limit as n goes to infinity. Notice this is all positive, so 5 over n plus 1. Well, as n goes to infinity, this fraction goes to 0, so this just goes to 0. Right, so that's L. And so remember, if L is less than 1, and I think that's the case here, right, because 0 is less than 1, we're in case A, which means this series converges. So this converges, right? So where does it converge? Well, notice that, right, it converges for any x, right? Because you just get 0 times x, so it doesn't matter what x is, right? So this converges for all real numbers, right? This converges, let me write it this way. It converges on the real number line for all real numbers. Okay. So I think that answers the question. Find the interval of convergence. It's from negative infinity to infinity. And the radius of convergence is, well, infinity, right? Right. So 0 minus infinity, 0 to 0 plus infinity. Okay, so I hope that helps. Again, that might have been an easy one to start, but let's do one more just to make sure you get the idea. Okay, so second example, this is also from the book. This is number 10. We want to find the interval and radius of convergence for this series here, right? So here my Cn is just negative 1 to the n divided by 9 to the n. So this is going to be an alternating series, right? But it's times x to the 2n plus 1. So the powers of x are only going to be odd numbers, right? So again, to find the radius of convergence, we still take the limit. N goes to infinity, right? And maybe I'll just remind you, right? It's Cn plus 1 over Cn, and it's going to be, well, all right, so x, so again, a is 0 here, so the numerator will just be, right, x to the power 2n plus 1, although this is 2n plus 1, right? And then in the denominator, it's just going to be x to the 2n plus 1. Right, at least in this example here. And I should have written down what the Cn and Cn plus 1 are, but we can do that now. So the Cn is just going to be negative 1 to the n plus 1 divided by 9 to the n plus 1. Sorry, that's a 9. And then when you divide by Cn, you just flip it. So this is 9 to the n divided by negative 1 to the n. And now let's look at the x's. So we have x to the 2n plus 2 plus 1 is 2n plus 3 divided by x to the 2n plus 1. Right? All in absolute value. And so when we simplify all this, let's see what we get. So first of all, this is negative 1 to the 1, right? Because the n's can't. Negative 1 to the n. Right? So this is just going to be negative 1. Of course, the absolute value will take care of that. And then divided by 9, because 9 to the n cancels, right? And then you're going to get, well, this is, right, x to the 2n plus 1 plus 2, right? So times x squared over x to the 2n plus 1. 2n plus 1, right? So these cancel, leaving you with just x squared. Right? So this is looking better. This is just going to be the limit as n goes to infinity. So an absolute value, negative 1, is just positive 1, right? So this is just x squared over 9. And that's my L here, right? So yeah, in this case, this limit depends on x, right? And if you remember the previous example, we got 0, and it didn't matter what x is. But here, this will matter what x is, right? So when does this converge? Remember, when L is less than 1. So we want this L to be less than 1, which means we want x squared over 9 to be less than 1, right? Oh, yeah, well, you can see that this doesn't depend on, so I skipped a step here. This doesn't depend on n, right? So this limit is, this L is just x squared over 9. Sorry, so that's the limits, right? And we want the limit to be less than 1, which means we want x squared to be less than 9, which means we want x to be between negative 3 and 3. Right? Remember, x could be negative, right? So that's our interval of convergence, right? From negative 3 to 3. And since we're centered at 0, the radius of convergence is 3. Okay. On the other hand, how do we know that it's the open interval, right? Notice that's why I didn't definitively say this is the answer yet, because we have to check separately what happens at x equals 3 and what happens at x equals negative 3. Right? Do we include the endpoints or not? Right? So let's look at what happens when x is equal to 3. So when x is 3, right, that's when L is 1. And remember, when L is 1, we have no idea. So we simply have to look back at the power series and see what we get here, right? So here's the series. So when x is 3, we're going to take the sum and going from 0 to infinity of, again, negative 1 to the n over 9 to the n, right? And then we have x is 3, so 3 to the power 2n plus 1. And I'm running out of space here, so let me do this. All right, so I'm going to scroll down a little here. All right, so what does that get us? That gets us the sum and goes from 0 to infinity. So we still have negative 1 to the n over 9 to the n. And then 3 to the 2n is 9 to the n, right? So this is going to be 9 to the n, times 3 to the 1, which is 3. So the 9 to the n's cancel. And we're just left with, and going from 0 to infinity, of 3 times negative 1 to the n. So does this converge? Well, think about what this is, right? The 3 can come outside. And now you're just alternating, right? This is just going to be negative 1 to the 0, right? So that's going to be 1, minus 1, plus 1, minus 1, plus 1, minus 1. So, of course, that doesn't converge, right? It just alternates between 1 and 0, essentially, right? So this diverges, right? This definitely diverges, right? But just by the nth term test, right? This limit here, the limit of negative 1 to the n, does not go to 0. So the series diverges, right? So we definitely don't include the positive 3. And at this point, I should really let you work out what happens at negative 3. Essentially the same thing, right? The only thing that changes here is that this becomes a negative 3. And so you still get 9 to the n, but then you get a negative 3 here. So the series still alternates, right? And so because the only difference is, it's negative 1 plus 1 minus 1 plus 1. So where the negative starts doesn't really matter. Either way, this diverges also, again, by the nth term test. So, so this was correct, as it turns out. The interval of convergence is the open interval from negative 3 to 3. We do not include either endpoint because the series diverges at both the left and the right endpoint. So I hope that helps figure out the interval and radius of convergence, right? You just use the ratio tests, right? And at least in these cases, the ratio test will always help you get the answer. Okay, next up, we want to recognize that a power series actually defines a function, which we'll call f of x, right? And so this is our power series, assuming it converges, of course. And the nice thing is that the domain of the function will be the same as the interval of convergence, right? Whether it's an open or closed interval, again, you have to check that separately. But let's say it's an open interval, then the domain of the function, right, will be the same as the interval of convergence. Okay. Another nice thing, and this might help if we write out what f of x is here. In fact, let's just call it y, right? So we have y is equal to, again, c0 plus c1x plus c2x squared plus c3x to the 4 let's do one more. C3 to the 3. I lost count there. C3 times x to the 3 plus C4 times x to the 4 plus dot, 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 right? All right. So that's right. So that's my f of x. And the nice thing when you do have a power series, and if it does converge, then this is going to be a continuous function, at least on its domain. And it's also going to be differentiable, right? So we can take the derivative. We can take y prime or f prime of x. And you can just do it term by term. Now that, you know the sum rule for derivatives, right? If you have the sum of two functions, then the derivative of the sum is the sum of the derivatives, right? And you know that works for two functions or three or four or five. But how do we know it works for infinitely many functions? That's, infinitely many sums. Okay, so that might not be clear, but it turns out that it works, right? That you can actually take the derivative of each term separately, right? So let's do that, right? This is going to be C1 plus 2C2 x, right? Plus C3 times C3, right? X squared plus 4 times C4 x cubed plus dot, dot, dot. Or if you want to write it as a sum, right? Notice, though, that this starts at n equals 1, not 0 anymore. This equals, this equals. Yeah, so this is the sum, n going from 1 to n, of n, right, times Cn times x to the n minus 1, right? So this is still, right, x to the 0 here, right? This is x to the 1. So, yep, this is the ordinary power rule for derivatives, right? And while we're at it, let's take the second derivative, because you're gonna need that at some point. So now the derivative of this is 0, so you just get 2c2 plus 3 times 2, so that's going to be 6 times c3x plus 4 times 3, that's going to be 12, c4x squared, and so on. Oops. Right. So that is going to be the sum going from, now we're starting at n equals 2 to infinity. So now we're going to have, right, n times n minus 1 times Cn times x to the n minus 2. Okay, so keep that in mind, that when you take derivatives, right, you're effectively shifting your n, right, because the c's start at 1 for the derivatives, and then for the second derivatives, the c's start at 2, right? So yeah. Okay, so let's go on to another property. This is, I guess some people, they call this the identity property. So this is the identity property. And all it states is that if this series, right, if this power series equals 0, right? In other words, if the function is identically equal to 0 for all x, right, at least on some interval, on the interval of convergence, or on some interval where this exists, right, not just as a single point. But if this is true on some interval, then we can say for sure that the Cn's have to be 0, right? All the Cn's, right? So for all n. Okay. And as a consequence of that, if you have two different series, let's say f of x is the sum n going from 0 to infinity, and let's use a different letter. Let's use an, x to the n. So obviously the a's are different here, right? And you have another series, I'll call it g of x, right? Say bn x to the n. So here we're just centered at 0, right? So if the two functions are equal, right? In other words, if the two functions are equal identically the same function on some interval, then we know that the ANs and the BNs have to be identical as well. In other words, the constants, the coefficients here, have to be the same, again, for all n. Okay, so keep that in mind. Okay. Next thing, we want to define a function to be analytic. So f of x, this function. So any function is called real analytic. Real analytic at a point, let's say x equals a, if the power series, I'll write it down again, n goes from 0 to infinity, of Cn x minus a to the n. If this power series exists and it converges to the original function f of x, right? So in other words, if f of x has a power series, right? If it has a power series representation, it's called real analytic, okay? And the book just says analytic, and that can be a little bit confused because analytic could include complex analytic, but we're not going to worry about that here. So I'll say real analytic, but in most cases I'll just say analytic, and that means real analytic here, right? Okay, and as a special case, let's look at what happens when the CNs, let's say the CN happens to be the nth derivative, the nth order derivative at a divided by n factorial, right? So then you have your power series will look like this. So n goes from 0 to infinity, and then you have the nth derivative evaluated at a divided by n factorial times x minus a to the n. And this should look familiar, right? This is specifically called a Taylor series. Taylor series, OR. Right. So a Taylor series is just a very specific power series with these specific C's, right? These are the specific C's here. Because in general, the Cn might not look anything like it. It has nothing to do with n factorial, right? The Cn's could be any constants. But if they're these particular constants, then it's called a Taylor series, right? And if a is 0, right? In other words, if the series looks like this, so if a is 0 here, and this is just x to the n, this is called a Maclaurin series. I think I'm spelling that right. And so, this might be a good time to bring up a list of some of the typical Taylor and Maclaurin series that you've seen in Calc 2. And here they are, right? So this is the list, and I got this directly from your book. So typical list of power series, Taylor series, and in particular, since we're centered at 0 here, these are Maclaurin series. And yeah, remember e to the x is just this particular series here, right? So it's just x to the n divided by n factorial, right? And so they list the first 4 terms of the series here. And these are the intervals of convergence, right? So the e to the x, of course, converges everywhere. So does cosine x, so does sine x. Notice this is not tangent, right? This is not tangent x. This is inverse tangent, arctangent of x, right? And so this is the power series for the arctangent of x. And notice the interval of convergence is the domain of arctangent, which is just from -1 to 1. Okay? So yeah, this has a very specific interval of convergence. Yeah, sorry about that. Okay, so, right, and then you have the hyperbolic sine, hyperbolic cosine. You can even have logarithm, right? Logarithm of 1 plus x. And if you want to take log of x, that's fine. right? You can write the power series for log of x. However, this is where you're going to have to shift, right? This is going to have to be x minus 1 to the n, and so this is centered at x equals 1. And so, yeah, so this would be a Taylor series. But to avoid all that, you can just have the log of 1 plus x, and that's a simpler series here. And this last one here, this, you might remember, this is the geometric series, right? Specifically called the geometric series. And it only converges between -1 and 1, right? So yeah, that's, and you can check the endpoints don't work because you get, it's, adding up a bunch of 1s, or you get the alternating series. Either way, by the nth term test, they would not work. So yeah, so this is just to remind you of this list of series here. It's in the book. Just keep it in mind going forward. Okay, so next example, right? This is going to be an example of what's called re-indexing a power series, right? So we're going to re-index the power series, right? So here's the example. We want to rewrite this as a single power series. We have the sum of these two power series. Here, n goes from 1 to infinity of n times cn x to the n minus 1 plus 3 times the sum, and going from 0 to infinity of cn x to the n plus 2. Okay, so yeah, this is going to happen quite a lot going forward. You're going to get a sum of a whole bunch of series. They may or may not even start at the same n, right? So here we start at n equals 1. The other one starts at n equals 0. And so, so how do we get this to be a single power series? In other words, right, we're going to have some series, right? And again, where it starts, we don't know yet, but it does go to infinity. And, the question is, what is the single form that we can write this in? Okay, so that's the idea here. So one way to do it is just to write out the terms, right? I mean, going forward, I'll show you a different way of essentially renaming the n's using a different index, say k. So we can do that. But for now, I'm going to write out the first few terms of each series, right? Let's start with the first one here. The first one, when n is 1, we have 1 times c1 times x to the 1 minus 1 is 0. Well, okay, x to the 0 is 1, so we don't need to write that. The next term is when n is 2, so we're going to get 2 times c2 times x to the 2 minus 1 is 1. Plus 3 c3 x to the 3 minus 1 is 2. Let's go on to the fourth term. When n is 4, we're going to get 4 times c4 times x to the 3. And one more. You know what? I'm going to run out of space, so we'll leave it at that, right? Plus dot, dot, dot. Okay. So now let's do this, the second term here. So notice that there's a 3 here. So if it helps, because it's easy to forget, I'm going to put the 3 on the inside, just so we remember that everything is multiplied by 3 here. Now remember, this also starts at n equals 0 instead of n equals 1. So now we start at n equals 0, so we're going to get 3 times c0 times x to the 0 plus 2. So this is x squared already, right? And then when n is 1, we have the same 3, c1, times 1 plus 2 is 3, so x to the 3. And then we're going to have the same 3 again. N is 2 now, so c2 x to the 4, plus 3c3 x to the 5. You get the idea. That keeps going as well, right? Okay, so now we have both series written out term by term. And notice that our goal here is to essentially write this in terms of the same power of x, right? X to the n. Now, how can we do that, right? Because the first series starts at x to the 0, x to the 1. The second only starts at x to the 2. So in fact, these two terms here are on their own. We're going to have to break those off separately. They can't be combined with the second series because well, the second series begins at n equals 2, right? So we're still going to have the c1 plus 2c2x by itself, right? Now, everything else here, all of this should be combined into a single series, right? Oh, that's a little messy. Yeah, so we're going to try to combine everything now, right? So what would the first term be here, right? So we're going to have the x squared term. The x squared term is going to have 3c3 plus 3c0. So 3c3 plus 3c0, all times x to the 2. And then moving on to the x to the 3 term, you're going to have 4c4, right, plus 3c1 times x cubed. All right. And I guess we can do one more. Now, I wasn't able to write it, but I think you get the idea. This will be 5c5, all right, for the x to the 4 term. And then here you're going to have 3c2 times x to the 4. And we can do one more, but I think you get the hang of it, right? So when we write this power series out, the first two terms are just left alone here, right? They're separate. But now we can index this starting at 2, right? So now let's write as a sum, n goes from 2 to infinity. Okay. And so what are the c's in the bracket here? Well, we're going to have 3, but notice that this 3 here is only for n is equal to 2, right? Then it goes on to 4, 5, and so on. So this is actually a variable here, right? If n starts at 2, how do you get to 3? 2 plus 1 is 3. So n plus 1 times c, and again, we're starting at 3 here, so this is also n plus 1, right? Plus, and then notice that this 3 here is a constant. That does not change. So that stays 3 times c. What's the index? What's the subscript here? 0. Well, how do you go from 2 to 0? You subtract 2, right? 2 minus 2 is 0, right? And then, so for n equals 3, you're going to get 3 minus 2 is 1, and so on, right? So these are the constants, and then you just multiply by x to the n. Okay, so that's our question mark here. This whole thing is the constant, right, times x to the n. So this is one way to rewrite a power series, a couple of power series as a single series, right? Typically, you do have this little dangler here, these terms in front, that just can't be combined into the series. Right? Maybe I shouldn't say always, but usually you do get these, but not always, right? And so then this is the series re-indexed, right? We're re-indexing, instead of starting at 0 and 1, we're now starting at 2 because we left these alone on the outside here, right? Okay. So let's do one more because this is something you're going to have to do over and over again in the next two sections. So let's do one more. Okay. So this is also in the book. This is number 30. We're going to rewrite this power series as a single series, right? So notice the first, there's 3 of them here, right? So there's this one. Oops. The second one is this. And the third term is this. Notice the first 2 begin at n equals 2, and the third one begins at n equals 1. Okay. So how are we going to combine these into a single series? So again, the goal, if you remember, is to group everything with the same power of x, right? Notice that here, this is all x to the n. It's the same power of x. So where would we start, right? So notice that here we're starting with x squared, but for the second series, when n is 2, this is n minus 2 for the exponent. That starts at x to the 0, right? And for the third series, you're starting at x to the 1. Okay? So the biggest power that's true for all three terms here, all three of these, is going to be n equals 2x to the 2, right? So just like in the previous one, we had to start at n equals 2. Okay, so eventually we're going to start with n equals 2. But notice that this first one here is going to start at 0. So let's bring that out. We're going to get, right, so for the n equals 0 term, what are we going to have? We're going to have 2 times, oh, I'm sorry, this is, yeah, it's x to the 0, but n is going to be 2 for the, right, for this term here, for the second term. Okay, n is 2, right? So you get 2 on the outside, times n, which is 2, times n minus 1, which is 1, times c2 times x to the 0, which is 1. Okay. Right. And then when n is 3, well, you're going to get 2 times 3 minus 1, which is 2, times c3 times x to the 3 minus 2, which is 1. Okay, so that's from the second series here, right? Oops, sorry. So what happens then with the third series? Well, we start at x to the 1. So for this one here, the last term, what do we have here? We have 3 times 1 times n times cn, which is c1, times x to the 1. Okay, x to the 1. Right. And now, all three of them are going to have the same power of 2, right? So the real trick now is figuring out what this last one will be, right? So we might as well start with n is equal to 2, right? Oh, actually, we're going to have to switch indices here, indices. Yeah, let's call it k, right? Let's call it k, right? So k is going from 2 to infinity now. Okay. So if k is going from 2 to infinity, notice that the first series, the n is the same here, right? So here, n is equal to k. It's the same thing. And boy, I'm going to run out of space very quickly here, but, right, so this is still k times k minus 1, right, times ck times x to the k, right, and that's just from the first term. Yeah, give me a second. I'm going to pull this down here. I'm just going to go on the next row, because you can see I'm going to run out of space very quickly. Okay, that's better. So yeah, so like I said, this is going to be continued down here. All right. So we did the first term of the series. Let's go on to the second term. The second term is the one that starts with the 2 here, so we need the 2. And right, so here, remember, this is n minus 2. If we want that to be our k, right, so n minus 2 is our k, right, which means n is really k plus 2, right? So this is not n anymore. It's going to be k plus 2 times n minus 1. So n minus 1 is k plus 2 minus 1, or k plus 1, times cn, but remember n is k plus 2, times x to the n minus 2. Well, n minus 2 is just k. So that's x to the k, and notice that's the same exponent as in the first term here, the first part of the series. Okay, so now we go on to the third term here, and plus, now this has a 3 in front, so the 3 stays. And what is, right, so this is going to be x to the 1. If we want to start it at n equals 2, is our first exponent, right? then our k should just be one more than that. K should be n plus 1, which means n is k minus 1. Right? Wait, did I get that right? So yeah, in other words, if k is 2, then n is, if k is 2, n is 1. Okay, I think that works, right? So then this is going to be, wait, hang on. Something's really wrong here. So if we're starting at, well, we're not starting at 1. We actually want to start at 2, right? K is 2. So we don't need any of this. Oh, I'm sorry, I'm confusing everybody here. Yeah, we don't need to re-index here, right? Let's just use n equals k. Right, n is the same as k here. So yeah, this is just x to the k, right? So this is going to be k times ck times x to the k. I don't think we need to re-index at all, right? The only difference is that we're starting at 2. We took care of what happens when n is 1. When n is 1, that's this term here. So that's separate. That's going to stay separate. Okay. All right. Sorry about that. I think this works, though, right? And notice that the x to the k is the same for all of these, so I didn't have to write these in each term. I could have factored that out, right? We could have pulled that out here and just write that. And so the rest is just really expanding all this out here. So again, right, we know that all of this is going to come in front, but right now I just want to take care of the terms in the series, right? So yeah, let's just multiply all this out here. We're going to have, yeah, so this is going to be k times k plus 1, so that's k squared minus k, right, times ck, right, and then plus 2 times, well, all of this, I don't think we need to multiply this out. So here's the ck, and here's another ck. So let's combine the first and the third terms, right? So so that's this down here. Now let's combine that with this, right? So this is going to be plus 3k times ck, right? And so that's what we can expand out here. This middle term here, I'm going to leave that alone. I'm not going to expand that out. You can, but it's not necessary here. Okay. Okay, so so now if we expand this out, we get k squared minus k plus 3, right? Oh, plus 3k, I'm sorry, plus 3k. This is all times ck. And this is going to stay the same here. So before we go any further, negative k plus 3k is really just 2k. So let me fix that. Yep. Negative 1 plus 3 is 2, right? So plus 2k. Yep. Plus 2k, right? Times ck. And then all of this here, right? So that's a plus, plus 2 times k plus 2 times k plus 1, ck plus 2, all times x to the k. And in fact, we can factor out a k here. I don't know if that's necessary, but let's do it. And let me leave some space for this first. In fact, let's write the first term here. What's the first term? It's going to be 4c2. Actually, yeah, okay, 4c2. So this is going to be 4 times c2 plus 6 times 2 is 12c3. 12c3 plus 3c1, right? And that's all times x to the 1. Now we can go on to the series starting at k equals 2. We're just going to have k times k plus 2 times ck plus 2 times k plus 2 times k plus 1 times c k plus 2 all times x to the k. Phew, that was a long one. Right. And again, sorry for getting a little confused here, right? I thought we were starting at n equals 1, but we're starting at n equals 2 for the series here, right? So yeah, we already took care of the n equals 1 in this first term here, and that ended up being the 3c1 here in front. Anyways, yep, that was a bit of a longer one. And of course you're going to, oh, sorry, that was the first one we did, 26, and then I did 30, which was a little bit longer. And so this is something you should really work at in 6.1, right? Do at least 2 of these. You know, you can do one with only 2 terms and then one with 3. So I don't remember how many that were in the homework like this, but yeah, you want to do at least one. I would suggest do 2 of these. You really want to get used to this. Because this is something we're going to be doing a lot of in the next section. So yeah, this is very important. I know it's a little confusing. Again, try to think about, well, if this was my previous n and I want a new n, think of your k as the new n. Right? So you're using k as your new value of n. And right, in this case, we wanted to relabel this exponent, the n minus 2, we just want to call it k, right? The same k as in the first term, right? So that shows you the re-indexing process here. And again, what got confused here is that, right, we're really starting at 2 because we took care of the one of this term here. We took care of that on the outside. So because we're starting at 2, then we don't need to change this. This will start at 2. So we simply rename n and just call it k instead of n. Right. Just to be consistent, because all 3 of these terms are going to start at k equals 2. So I hope that helps. I hope I didn't confuse you too much here. But yeah, so this re-indexing process here is something you're going to do a lot of. And you know, next time we do it, maybe I'll do it one more time carefully, but once you get used to it, it's really not that bad. So that, I think that's it for 6.1. Maybe I'll mention one more thing about the power series here. You can have a power series, or well, you can have an infinite series. Well, a power series is an infinite series, right? Because if it terminates, it's just a polynomial, right? So you can have a function that you can get by using, let's say, a Maclaurin series, right? So you have the nth derivative at 0 over n factorial times x to the n, right? And so just by taking the derivatives and plugging in 0, you get the coefficients, right? You get each coefficient for each term. And so if you have a function with infinitely many derivatives, you might think that when you form this series here, when you form this power series, that has to converge. And in fact, it should converge to the original f of x. Unfortunately, it doesn't always work that way, right? You can have a power series like this, a Taylor series specifically, that you form into a power series, and it might not even converge at all, right? So there are cases where this does not converge, right? And then even worse, there are cases where this does converge, but it doesn't converge to f of x. It converges to some other function. Confusing, right? Fortunately for us, we're not going to worry about that. For our purposes, when we form a power series, it will either converge, and you can find the interval of convergence, or it just won't converge, in which case it doesn't help us at all, right? So the point is, going forward, when we solve differential equations, we are assuming that we have a series that can be written as a power series, right? So we're going to assume that our solution, our f of x, right, or y, can be written as a power series. And the danger in that is that that's not always true, that you can't always write a solution as a power series. And if not, then you can't use this technique. You cannot use the technique of power series to solve differential equations. Although, well, okay, let me say one more thing here. You can also form an infinite series. It doesn't have to be a power series. And if you can form an infinite series of these and write it as a function, then that's almost just as good. In fact, it really is just as good. So for now we're concentrating on power series, at least for this section and the next section. Then when we get to 6.3, we're going to expand our series. These might actually not even turn out to be a power series. A power series is more specific than an infinite series. Okay, so we'll get to that in 6.3. But for now, we're assuming that we can write our solutions of differential equations as power series. And in the cases that we're going to deal with, that won't be an issue. It's going to work out. It's going to work out. And if it doesn't, then we'll quickly see why. It's possible that this might not converge, right? And if it doesn't converge, then it's not going to work out. But that's pretty rare. For us, it's going to work out because, it's a textbook and they give nice problems. So I hope that helps.